Okay, so it's 3:20, so I'm going to start my talk about technical deep dive into the Sokovan scheduler. So, Backend.ai and the Sokovan scheduler is a container-based workload orchestration and job scheduler, but it does not use Kubernetes, but it directly runs on top of bare metal environment or Linux virtual machines. So it is highly optimized to batch-oriented jobs, especially for HPC and AI training workload, but it also hosts dynamic and interactive workload and inference workload as well. So, Backend.ai, the infrastructure stack covers a very wide range of the technical problems in this area. So, the infrastructure management and workload orchestration, we have a very two famous frameworks. One is a Slum, which is used by many supercomputing and HPC clusters, and Kubernetes, which is used for many cloud-native deployments of microservices and web applications. And we have AI ops and ML ops stacks as well to provide the pipeline like automated job execution for like multi-stage training and so on. And we have an application layer which packages like a full-fledged AI runtimes and frameworks as a single package. Backend.ai covers all these areas just on top of the very hardware-centric infrastructure layer. So Backend.ai with the Sokovan engine covers the workload orchestration part. And in this talk, I'm going to focus on the Sokovan engine. So we started to build the Sokovan orchestrator in 2015 when the Kubernetes was in very early stage. So actually we have built everything from scratch to make reproducible computing environments for researchers. Actually, our CEO, Joongi, has a PhD in physics, and he researched complex systems and brain signal analysis with some early neural network technology. And he also managed like 1,000 node computing cluster in the physics department of Postech. We realized that the management of such large-scale computing cluster should not be done by humans. After finishing my PhD in GPU accelerated packet processing frameworks, I joined with Joongi, and we started to build something based on the new technology, containers. So containers are actually a very thin virtualization layer that allows direct access to hardware acceleration technology, but it has some limitations in full isolation between the multiple tenants. We focused on building custom sandboxes and GPU virtualization to isolate multiple tenants, and we have built the base technology around 2018, and we began to deploy this technology to our enterprise customers like Samsung Electronics and like Hyundai Movies and other like big enterprises in Korea. 2019, and we got the DGX ready software validation from NVIDIA, and we started to fully support the GPU direct storage for multi-tenant container-based environments since 2022. So we now also expanding our scheduler to support multiple various heterogeneous AI accelerators as HyperXL just presented before. Our key features are based on there are multiple factors of this scheduler. So the first part will cover some core concepts of the Sokovan scheduler, and then I'm going to go through key technical differentiation compared to other schedulers as follows. So the core concept is we abstract workload as a two-level job units. So the top level job unit is a section which represents our job pod group or some kind of abstract workload, either interactive batch or inference. And the corner, which is mapped to individual containers, and it represents the minimum schedulable unit of the workload. And we have the concept of resource group, which is mapped to node pool in the Kubernetes terminology, which is a logical collection of the compute node having different quota and access control configurations. And we have a special feature to split a single physical node into multiple resource groups so that we can partition a single node into multiple devices to schedule different type of jobs. For example, training for the first 4 GPUs and the inference for the rest of 4 GPUs. And we have built this scheduler to be scalable because we targeted to run like a job consisting of multiple hundreds or thousands of GPUs scattered across hundreds of computing servers. So we, by design, we applied gang scheduling by default so that we could synchronize the life cycle of the multiple containers spawned in different nodes. And we also added automatic retry for the partial failures and transient failures, with some configurable threshold. And we implemented this to have responsive reconciliation continuation by combining polling and events all together, so that we could make it to ensure liveness over a long time when there are occasional hardware failures, but we also wanted to make it respond fast to make everything respond as quickly as possible. And overall, all the state transitions in the scheduler of when there are thousands or hundreds of computing sessions and kernels, we batch the state transitions periodically so that the system does not crash due to some database transition failures. We have 2 crucial multiple stages in the scheduler. So the first one is the job sequencer, which implements the actual job queuing and scheduling strategy, like a heuristic FIFO, which implements head-of-line blocking avoidance, like a backfilling in Slum, and dominant resource fairness, which is also balances resource usage between different type of resources, for example GPUs and CPUs. And you can also plug in your own custom scheduling mechanism using our structured API interface. And we have an agent selector, which also can be refreshed as a node selector, which implements like a bin packing or balanced distribution strategy, where you can also configure, write your own metric-based placement strategy as you want. And we do have a first support for job priority and job graph, so that you can pipeline multiple jobs all together and spawn them at once and make them complete as quickly as possible. And we do support virtual clusters, which is based on Docker overlay and the Selenium, which is directly integrated to our Sokovan engine, so that you can have virtual private clusters for your sessions where multiple containers distributed across different nodes. We also provide multi-layer networking. So this is actually the most complicated part when you design AI clusters. So in conventional web application stack, you only have to consider a private network and public-facing network with some privately spawned databases in the backend. But when it comes to AI and HPC workload, you need to consider east-west traffic, which means that you need to optimize or increase the available bandwidth between different service nodes because they have to talk to each other to do some distributed training or computation. So in that sense, we have many different technologies like RDMA over conversion Ethernet, RoCE or RoCE2 or Ultra Ethernet or InfiniBand. All those new technology and networking must be incorporated into your system design. And also for the storage part, our partner just behind Fox Data, we also need to fully support the GPU direct storage and other acceleration to feed the data without any bottleneck to the GPU to sustain the GPU's high performance. So When you configure virtual clusters on top of a Sokovan engine, we have pre-configured environment variables so that you can just write down your automation script to, and you don't have to modify your code every time when you change the configuration. So, for example, you can refer the cluster size and the cluster mode and the host name to connect with automatically configured randomized SSH key to individual containers and so on. All these things are automated. You don't have to think about like additional configuration for RDMA, NICs, and NCCL and things like that. Everything is automatically overset. Inside the computing node, we have a multi-stage resource allocation after finishing job sequencer and agent selection. So inside the individual computing node, we call agents. We have a topology-aware resource mapper, which fully supports NUMA nodes with arbitrary numbers, and also GPU and network card mapping considering the topology. So, for example, you can change the topology place policy, for example, interleaving or concentrated, so that you can intentionally distribute your CPU mapping and device mapping for multiple different NUMA nodes, or concentrate to a single one for maximum performance. And we have a special resource slot and type abstraction, which can be conceptually mapped to Kubernetes DRA, dynamic resource allocation. Actually, we designed this abstraction like 6 years ago, and still we are using it very well for adding new devices like Hypixel and other AI accelerators. So I just included two examples of the CPUs and the NVIDIA GPUs. So we have multiple different types for both discrete device allocation or fractional device allocation, which can be represented as integers or decimal values. And we also have a special types like unique, which allows mapping only one single device per container for NVIDIA's MIH devices. And also we have a unified resource slot, which is directly mapped to the host memory, so that we can represent like situations like where CPU and GPU memory are fully shared together and the constraint under the same single resource constraint together. So this applies to NVIDIA's JSON platform and the DGX Spark cases, as we have demonstration on our booth. Yep. So let's summarize the talk. So Sokovan is a very performant, customizable topology-aware container-based workload scheduler specifically designed for HPC and AI workloads. It is open source, so the full scheduler implementation, you can just look up the GitHub and the level of backend.ai to see how it is implemented. And it has all the state-of-the-art features for multi-node and multi-tenant and batch scheduling. It supports various types of workload hosted concurrently, interactive, batch inference. You can configure each resource group to run a specific type of workloads only, or mix and match all these workloads together as you want. And Sokovan and backend.ai platform provides a consistent user experience across heterogeneous accelerators, and with a universal resource slot abstraction that can be applied to many different types of accelerators as listed. So it can virtually express all kind of AI accelerators in the market, and it provides the solid foundation of sovereign AI stack when you need to be future compatible of your choice of AI accelerators. That's all of my talk, so thank you. Yeah, thank you for coming by.